For our next example, I want to look at a ladder leaning against a wall and try to figure out what the coefficient of friction between the floor and ladder needs to be in order for the ladder to not slip. So here we have our ladder, 2 meters long. It's got a mass of 18 kilograms, and it's resting at a 60-degree angle with respect to horizontal. So what you typically do with torque problems is choose the lever as your system. That's really what we're interested in. So whatever it is that's going to be twisting or torqued, that's your system. And then the surroundings are all those things that are exerting forces on it. So I've already drawn my free body diagram with all of the forces, and I've drawn it to show that the system is in equilibrium. All of these forces added together should add up to 0. And now let me go ahead and draw in my extended body diagram. So for this, we just do a very simple representation of the system. Just use a simple line and then apply all of the forces at the location that they actually occur. We're going to use this for deriving our torques. The free body diagram gives us our net force. The extended body diagram gives us our net torque. So at the center of mass, we have F grav downward. At this point down here, we have an upward normal force, and I'm going to call that F. That's the normal force by the floor. We also have, I'm just going to use lowercase f to indicate friction. And then up here, we have Fn W, the normal force by the wall. Now, in real life, we should actually have a frictional force here pushing up on that ladder. But for simplicity, I'm going to go ahead and assume the frictional force on ladder by wall is much, much smaller than F and F, the normal force on the ladder by the floor. Another way of saying this is the floor is essentially carrying most of the downward force, and the frictional force really isn't playing that role. And if you've ever stepped on a ladder, you know that in most cases that frictional force really is not very significant. So right here I have all of the forces that I need, and the next thing to do is just choose my pivot point for calculating all of my net torques. But first, let's go to the net force equation. And from the free body diagram, I have that F net is equal to F grav plus F and F, normal force by the floor on the ladder, plus the frictional force, plus the normal force, plus the normal force by the wall on the ladder. So let me go ahead and actually write these out in terms of the magnitudes and unit vectors. The magnitudes are the unknowns. The unit vectors we can deduce from the problem, but the magnitudes are what we don't know. So F grav is going to be mg times 0 minus 1, 0. I could have just easily written this as 0 minus mg 0, but I just want to be very explicit as I write this out. Now, the normal force by the floor, that is in the positive y direction, so that's going to have a unit vector of 0, 1, 0. The frictional force, we can write that as mu times normal force by the floor, only this one's in the, if you take a look here, positive x direction. So that's going to be 1, 0, 0 for my unit vector. And then the last one is the normal force by the wall. And looking at the free body diagram, I see that this is in the negative x direction, so it has a unit vector of minus 1, 0, 0. And then let me just combine these all into a single net force. So F net is equal to, let's see, the x components. We have mu normal force of the floor on the ladder minus F, the normal force of the wall on the ladder. In the y direction, I have, let's see, the normal force by the floor minus mg. The z component is 0. So breaking these two out, since the net force has to be equal to 0, 0, 0, since we're in equilibrium, I can see right away that mu times the normal force of the floor is just equal to the normal force of the wall. And the normal force of the floor on the ladder is just equal to mg. So, unfortunately, this doesn't help us calculate mu. We don't have quite enough information to find what mu is. So we need another set of equations. And we're going to get those from our extended body diagram. So, torque net here. And actually, rather than doing this as a vector, let's do this as a scalar equation. And the reason I can do this is, since I've drawn everything in the xy plane, all of my torques are either going to be in the positive or negative z direction. So I'm essentially doing vectors here, but I'm skipping a whole step just to simplify things a little bit. So anything that is causing a torque in the counterclockwise direction gives me a positive torque. That's because r cross f, my thumb would be pointing out in the positive y direction. Anything that goes in the clockwise direction, well, just think of it this way. R is along here, point your fingers that way, curl your fingers in the direction of F. Your thumb should be pointing into the screen in the negative Z direction. So I think I may have been saying positive and negative Y. What I really should be saying is positive and negative Z. Once again, I've forgotten to draw my coordinate system very carefully. So positive X is that way, positive Y is that way, positive Z is out. So I'm sorry for any confusion there. So let's go ahead, and first thing I should do is pick a pivot point. So there's three obvious choices. I could choose this end here, the center of mass, or this end right here. And I might be tempted to choose this end right here because it's got two forces. Choosing it as a pivot point makes those torques 0. Unfortunately, we want information about this friction force, so that might make that difficult. However, one thing to note is that going down here, if I can find what this normal force by the wall is, I have a way of figuring out mu. So I am going to go ahead and choose this as my pivot point, because even though that gets rid of this friction force, that's going to allow me to find this guy. I could have picked the center as a pivot point, thinking to get rid of gravity, but gravity is the one force that we know, and it's probably not a real great idea to do that. However, choosing either of these as your pivot points would still allow you to solve. It just would have required a little bit more algebra on your part. So the normal force of the wall causes a positive torque. So that's going to be the full length of the ladder times F, normal force of the wall. The torque by gravity is only at half the length, L over 2, and it's going to be negative. So we get a negative L over 2 mg. Now, this needs to be equal to 0, so solving this, the normal force of the wall, notice that the L's actually go away, and this is simply going to be mg over 2. And that makes sense. This force has twice the lever arm that the center of mass does, so it only has to push half its hard to hold things up. All right, so going back to this equation right here, let's see, I can plug in mg for the normal force of the floor, plug in mg over 2 here. I get that mu is equal to mu times mg is equal to mg over 2, divide through by m, divide through by chi, mu is equal to 1/2. So let's go ahead and quickly check our answer. Well, mu should be unitless, and it is. So the units do work out. The mg's cancel one another. How about size-wise? How can we go ahead and check that? Well, first off, typically mu is going to be less than 1. Sometimes we do have some very sticky surfaces where mu is greater than 1, but for the most part less than 1. So 1/2, just based on our experience, is fairly reasonable. But let's see if we can come up with something a little bit more substantive. And what we can do is go back to the free body diagram, to the extended body diagram, and choose a different pivot point and see if the results work out. So just for simplicity, let's choose, how about this point right here as my backup pivot point. That means gravity will exert 0 torque about that point. These two forces are both exerting a torque in the positive direction, and I'm just going to call this distance here d. It's L over 2, but just for simplicity, let's call that distance d. So the net torque about that point is going to be mu F normal wall times that distance d plus this is the floor. This is floor, not wall. This is wall times d, and in the minus direction, it's going to be F, the normal force of the floor, times d. Does this in fact equal 0? Well, this term right here is mg over 2 times d. This term is 1/2 mg times d. And this term right here is mgd. Sure enough, we get 0. So answer checks out. I'm pretty happy with that.